D-Wave, which is a company that I don't really know much about, but they specialize in quantum computing, announced general availability of Advantage 2 quantum computer, their most advanced and performant system, which is a quantum computer that you can access over the cloud. They're offering cloud compute. Customers can now access Advantage 2 system via D-Wave's Leap real-time quantum cloud service, which is available in more than 40 countries and offers 99.9% availability and uptime, sub-second response times, and SOC 2 Type 2 compliance to meet enterprise needs and security requirements. That Type 2 compliance is the one that's harder to get because it involves more over-time observations and things. So that's neat that it's been SOC Type 2 compliant. And this new system offers a 40% increase in energy scale and a 75% reduction in noise, which contributes to higher quality solutions for complex calculations. Because noise is the real enemy in quantum computing. And we'll talk about why in a moment. But what did you get?
I'm just wondering, though, this is the stupidest remark in the world. But I guess when it comes to quantum computing, you're really only offering SOC 2 Type 2 compliance within this universe, because the whole idea of quantum is that you're tapping into a multiverse way of thinking about things that has every infinite possibility, and then you're snagging the right one and pulling it into this version of reality.
So what you're saying...
So in every other version of reality, there could be a data breach because of what you did.
Yeah, you're saying that while the qubits are in superposition, it is not SOC 2 Type 2 compliant. Right. But once you collapse that, it seems to remain so.
Yeah, but you may be screwing over a version of you in every other reality.
That's wicked funny. And then D-Wave actually isn't the only one to do this. NVIDIA recently announced that they are opening the Global Research and Development Center for Business by Quantum AI Technology, G-QUAT, which hosts ABCIQ. I feel like we've gone back to the early days of computing with how we name these things. But they've powered the world's largest research supercomputer dedicated to quantum computing. So talk about messing with different realities, Perry. It's in Japan. It features 2020 NVIDIA H100 GPUs interconnected by NVIDIA's Quantum 2 InfiniBand networking platform. And Tim Costa, Senior Director of Computer-Aided Engineering, Quantum, and CUDA-X at NVIDIA, said, seamlessly coupling quantum hardware with AI supercomputing will accelerate realizing the promise of quantum computing for all. NVIDIA's collaboration with AIST will catalyze progress in areas like quantum error correction and applications development, crucial for building useful, accelerated quantum supercomputers. So things are moving quickly on this front. And so I think it bears taking a second to very abstractly talk about differences between quantum and classical computing, which I do not want to pretend I'm any kind of an expert on, but I went down a rabbit hole and tried to build as much of a good little simplistic metaphor understanding as I could. So I want to share that. In a traditional computer we're all familiar with, it executes instructions, right, in a linear fashion. You have a series of, you do this, and then you take the result and you do something to it. It's based on information stored as bits of ones and zeros. The simplest way to imagine encoding that is like if you have a grid of graph paper and you draw a smiley face just by filling in squares, any individual square on that grid is either a 0, empty, or a 1 filled in, and you've encoded something meaningful by drawing a smiley face just by filling in squares. That could be represented as binary. But you would read that in sequence by iterating through all of those grids, whereas a quantum computer starts with a field of quantum bits in superposition where they're in a stable state of being both 1 and 0. Then you engineer interference patterns by controlling the relative phases of the probability amplitudes of those qubits collapsing into either 1 or 0 when you measure. And then you set them all off so that they interfere with one another, collapse that superposition, and observe the results. And that is probably hard to understand just through hearing it. But the metaphor that I workshopped is, imagine you have a shallow pool of water, and all around the edges are different little wave generators that you can control. And you can time carefully when each generator creates a wave so that they all interfere with each other in the water. Some of them add up and get taller. Some of them subtract from each other and get smaller. And then imagine you suddenly freeze the pool of water, and you can measure the height of it at specific points to get information from it. So, to use a similar example to the smiley face, you could carefully do it so that the waves maybe create a smiley face by carefully timing how they all interact, and then you freeze the pool at that exact moment. It's way more crazy than that in practice, But basically, they work by encoding like the mathematical structure of a problem into quantum states and then watching patterns evolve and form in parallel. It's more like diffusion and less like brute force parallel searching or iterating through an instruction set. This breaks cryptography, which is, I'm sure, where you've probably had the most experience with quantum computing, right?
Absolutely, and that's the thing that a lot of people in cybersecurity are worried about is once you get more predictable, easy to use systems like that, then cryptography as we know it starts to get broken. And the whole nature of trust in the internet and security is built around cryptography. So the ability to protect things that need to be protected and make it to where people can't see or access things that shouldn't be able to see or access those things.
And it's because a lot of our cryptography relies on the exchanging of secret keys, which are just complicated numbers. Typically, like the example I'll pull on is RSA, where it's you have two prime numbers, so they only have the factor of 1 in themselves, and you multiply them together to get one bigger number that is not prime. It's really easy to multiply those two together, so if you know one of them, if you have them, you can exchange them. But if you just have that big, long, non-prime key, finding all the factors of it and then finding those two prime factors that created it is really difficult for a classical computer. But when you put that kind of a math problem into a quantum computer, it can essentially look at it more like a graph, like a big old waveform of how that number shifts and changes. And then it's really easy to find the point where the primes are. Like you literally watch the periodicity of it. And there's spikes and you, boom, encryption broken.
Yeah. And I think the saving grace with quantum right now is setting up a quantum experiment is very, very tedious, and you really have to know the thing that you're trying to solve for. So it is the age of punch card computing on steroids.
Yeah, it is. And it is still, I mean, I don't know if I would say in its infancy, but in its gangly teenage years. But like we are seeing a cloud provider offering quantum computing services now. And so like now is, and it has been, the time to prepare for a post-quantum world. So Microsoft has brought post-quantum cryptography to Windows in an early access rollout. This is from the Quantum Insider. Microsoft is pushing ahead with its plan to prepare the digital world for the threat of quantum computers by releasing early support for post-quantum cryptography on Windows and Linux systems. The move represents another step in Microsoft's broader security roadmap to help organizations prepare for the era of quantum computing, an era in which today's encryption methods may no longer be safe. Yada, yada. They're trying to resist future quantum attacks. Something that's interesting that never occurred to me is that one of the things they're trying to push for is to fight against this strategy known as harvest now, decrypt later, where people are capturing encrypted blobs of data that they can't read now.
Yeah, exactly.
Yeah, but once you have a quantum computer, break it, decrypt it. They've pushed this into Windows Insider Canary Channel. So this is coming down the pipes slowly but surely. There's a couple other implications, but I want to get your thoughts real quick.
Well, and I think that there are a lot of people right now that are assuming that some large governments around the world are trying to outpace a lot of the private company quantum computing work because of that idea of they've harvested tons and tons of data. You know, we know like China has harvested a lot of critical data from here in the U.S., like from the opium breach and other very large scale breaches. So a lot of that really hard to get to. You can have a supercomputer just kind of churning on trying to break that cryptography for years and not really make a lot of progress. But if you have an advance at quantum at the right time, then all of a sudden all of that opens up. And now every type of information operation that you wanted to use that data for is fair game. And so I do think a lot of us wonder like what's going on in dark rooms and, you know, subterranean warehouses around the world with some of the largest governments that have just money and brain power to throw at this.
Well, and maybe you can speak to the empirical truth of this, but my sense is that we've never really considered the encrypted blobs of data to be particularly sensitive. Like we would think, oh, well, if you intercept this, it's encrypted. You can't read it anyway. So we didn't do anything particularly to prevent people from grabbing encrypted blobs, except in like high security things. Unless
Yeah, I think some people have approached it that way, and some vendors and some organizations do. those of us that have been thinking about that problem for a longer time have known that even having the encrypted data can pay off as soon as somebody is able to break that. But when it comes to like the idea of a data breach, the thought there has always been if somebody grabs data that's encrypted using one-way encryption, especially, then that's not really a breach. It's when they get plain text data or easily decrypted, very, very weak encryption, that starts to constitute a data breach. And we're going to get to the point very, very quickly where regardless of what data was pulled, whether that's encrypted or not, whether that's using weak encryption or strong encryption, the contents of those data blobs are going to be vulnerable.
Yeah. And that's a scary thing to think about. And fortunately, it's the asymmetric encryption that is more easily broken by quantum computers.
Right.
There are still classical symmetrical encryption methods that become, I think, a square root of easiness better. I think I was looking at the equations earlier and trying really hard to parse them. But like quantum computing doesn't immediately defeat all of them. But like the original RSA encryption would take a classical computer thousands of years to brute force and a quantum computer like minutes,
Yeah.
So as we prepare for this future, one little last mention to wrap us up of the technical hurdles. Even as Microsoft opens the door to early PQC, post-quantum cryptography experimentation, the road to full deployment will be slow and complex. The new algorithms often require more memory and processing power than classical encryption methods. This could be a challenge for devices with limited resources, especially in sectors like mobile, embedded systems, and industrial control. And that last one, industrial control, is always the most worrying one, right? Because those subsystems are the most critical to society.
And they're really the hardest to do critical updates in too, because they do control things that society needs in order to function. And so if you do an update and it breaks something, that's catastrophic.
Yeah, it's way worse. So entering the brave new world of quantum, at least we're talking about this and preparing for this. It only remains to be seen how it goes. I want to talk to a quantum computing expert and try and get a better intuitive understanding of this, because I think it is fascinating to imagine solving problems this way using wave functions and interference. That tickles my audio engineering brain,
We can definitely make that happen. I know a couple people to reach out to.
Ooh, so stay tuned for that. That's exciting. Coming up next, something a little less technical and a little less successful, it seems.
Yeah, a little bit kludgy when you try to run an entire company with AI agents.
Ooh, stay tuned for this.